Listen, I will begin with a word of prayer. Let me stop distracting us. Heavenly Father, we thank you for this day. I thank you for students. Just ask you to help us to use this time wisely to prepare for the exam tomorrow. Lord, in your name I pray. Amen. Okay, guys. So I posted a solution to much of the math battle. Is there anything you guys would like to talk about specifically? I'd prefer to focus on integration today. I've spent a lot of time talking about parameterization Friday, so we probably should talk about integration today. What are the three major integration techniques that you need to have pinned down for tomorrow? Integration by parts, yeah. Partial fractions, and trig substitution, and combinations thereof, right? How about the hyperbolic substitution, yeah? It might be good for us to do the problem on the math battle that I didn't get a chance to write the solution up of. What was that one? Do you guys remember? Oh yeah, you don't have your math battles. I mean, did I post it? Yeah, I think I posted the statement of the math battle back when? Thursday? Wednesday? I forget. It's been a while. And I haven't solved this problem, but we could try. Yeah. Clicked the wrong thing. Seems like the internet has been destroyed so many times lately. I don't understand how anybody can still destroy it. It seems like every other day somebody's destroying the internet. And yet it still works. Weirdest thing. The integral of what is it? Inverse tangent of e to the x. dx over e to the x. I have to give credit where credit is due. This is a Dr. Sprano production. Let's see here. So the initial move, if we let u equal to e to the, u equals e to the x, I think is actually helpful. That makes, make a w actually. W equals e to the x, then dw. Of course, is e to the x dx. And that brings us to the integral of, let's see here, inverse tangent of w, and then what? Oh, look, so this says that dw over e to the x equals to dx. I don't know how to. Just don't be confused. Just okay. What should we do here? See here, I'm thinking kind of slow today. I'm gonna write down w, and then what's my dx? Yeah, dw over e to the x. Well, that didn't help. Didn't help at all. Huh. I feel like something may have been lost in translation here. You know, if this is e to the minus x, this problem is much nicer. Then what happens? Let's work that problem. Then this is e to the minus, what is this? Minus e to the minus x dx. And what happens? I think if I put a minus there, this problem becomes reasonable, because then this is what? Yeah, it's minus inverse tangent of w dw. Yeah. Did any of you manage to solve this one? You think so? Yeah. All right, well, I'll have to look at it. Good, good, yeah.
I didn't do the problem because they did, but what if you, when you had like dw over e to the x plus dx, you just make dw over w?
What are we talking about?
Like when you had, without the e to the negative x in there, when you did your substitution, like could you use w twice and you get like inverse tangent of w over w squared?
Yeah. Does that work out?
I have no idea.
I mean, that's what I was getting, which is why I bailed on it, because it's not what I remembered. So I feel like I made a typo writing the problem down. But fair enough. We could entertain that problem. I mean, you have, many of you. The question is, can we go forward from there? Maybe, maybe not. I'm going to work on the e to the minus x problem. So this one, minus the integral. So what should I make here? That's my u. This is my dv, right? So I have minus w inverse tangent of w plus the integral of v du, which is what? W dw over 1 plus w squared. Am I right? I think so. And so, oh yeah, this is not the one Sprano told me. This one's too easy. Yeah. Yeah. This one, I bet that wasn't a typo. Let's continue on. I got scared off too easy. All right. So there's the solution to that problem, which was not on your math battle, but I mean, is not a. I wouldn't say this is an easy test question. I would say this is like a moderate test question. All right. So how about this? Now what are we going to do? Now that I have decided not to despair and give up on it, how about, if we believe Liate, we're going to do what? We're going to put u equal to inverse tangent of w, and that will make dv what? dw over w squared. Oh yeah, this is it. So du is dw over 1 plus w squared, and v is minus 1 over w. Yeah. This is the goodness. This is the problem. So we got, oops, uv minus integral of v du, right? In this context, that is, what we got? Minus 1 over w, inverse tangent of w, minus the integral of minus 1 over w times dw over 1 plus w squared. I'll clean it up one more step here. This is minus 1 over w, inverse tangent of w, plus the integral of dw over w times 1 plus w squared. And that's why I like this problem, is because it, first of all, it involves kind of a natural u substitution if you can just get over the horror of what happens after you do it, right? Then integration by parts is natural, but it leads you to something that you probably wouldn't have known how to integrate before you took this course, right? How do we do that, though? What's left? W times 1 plus w squared. Yeah, I'm trying to find a spot to do it. I guess I'll do it here. Partial fractions, right? So I should let 1 over w times 1 plus w squared equal to a over w plus bw plus c over 1 plus w squared. We need to work this out, right? So we have 1 is a times 1 plus w squared plus b w plus c times w. And so what's that give me? Well, if I put in w equals to 0, that gives me 1 is equal to a. If I put in w equals to 1, what do I get? I get b plus c equals to minus 1 as an equation. Let me call that star. And let's put in w equals to minus 1 because that should give us a kind of nice equation too. So that gives me that b minus c equals to, well, minus 1. Call that star star. What happens if you work with star star and star? If we add equations, what does it give us? Yeah, I get 2b equals to minus 2. So b apparently is minus 1. And what's c then? Minus 1 minus b. Oh, if I add these, if I take the difference of these equations, I get c equal to 0, right? All right. So going back over to here, we have minus 1 over w, inverse tangent of w, plus the integral of, after this little bit of algebra, we can see that is actually, a was 1, so 1 over w, and b was minus 1, so minus w over 1 plus w squared dw. So we get minus 1 over w, inverse tangent of w, plus the natural log of the absolute value of w, minus 1/2 natural log of 1 plus w squared, plus a constant, making the natural substitutions there. And then, of course, at the end of it, we have to go back to what? X, right? So w is e to the x. So the answer is 1 over e to the x inverse tangent of e to the x plus, oh, what's the natural log of e to the x? X. What's the absolute value of e to the x? E to the x, right? So this natural log absolute value w just simplifies to natural log of e to the x, which is x. Yep. Minus 1/2 natural log of 1 plus e to the 2x. So the question was, why was that there? Can somebody explain why I did that? Why is there a half there? U equals what substitution? 1 plus w squared. So make a substitution with the denominator. I'll do it. Let me do it where it's not so crowded. So if I have integral of w dw over 1 plus w squared, I could make it, let's say, h equal to 1 plus w squared substitution. Then dh would be 2w dw. So this becomes the integral of 1/2 dh over h, which is 1/2 natural log the absolute value of h plus a constant, which is 1/2 the natural log of 1 plus w squared plus a constant, which is what I did over there. It's just making a denominator substitution. Yeah. Yep. Ah, you mean this part? Yes, there is. Thank you. Other questions, concerns? So, to contrast, more or less the hardest thing that could appear on the test, right? This kind of thing. It's about as hard as it gets, I think. Kind of moderate, right? Where was that thing? If we look at the solution here, I would say that these are, if I have to decide on a difficulty level, if I had to grade the difficulty, I would say number one, A, this is an easy to moderate question. All right, this is pretty much straight integration by parts, right? That should not be surprising at all, that one. Part B might catch you off guard, but again, I would say that's actually easy to moderate. If you just hack away at it, you should get this one, right? I don't think we actually covered that in class, as it happens, right? But we did lots of stuff kind of like it, yeah. C is pretty straight down the middle, right? We should knock that one out of the park. And D, I would say, is moderate, but it shouldn't be surprising. We have talked about the integral of cosine to the fourth. So these ones, let's see here, cosecant. Well, we had such fun with secant, I decided to do the same trick for cosecant. It worked, right? So u equals cosecant plus cotangent works out. What would be the other way to do the integral of cosecant? How else could you attack integral of cosecant if you didn't have this flash of inspiration to u is equal to cosecant plus cotangent? What is cosecant? I'm dropping the 3 because that's just noise. All right? what would be a natural thing to do here would be just multiply by sine over sine, yeah? Why would I do that? Because I know that I can take a sine squared and I can convert it to a cosine squared, right? But it comes at a cost, which is what? It comes at a cost of 1 minus the cosine squared, right? But with that adjustment made, we could do integration by we could make a substitution, right? We've got a du over u squared minus 1. So here u equals to cosine. Du is minus sine of x dx, right? And so I distributed the minus into the denominator to make things prettier. Then what would you do? Yep. Oh, yeah, you guys know too much, but yes, that is tangent, inverse tangent, right? Give yourself an inverse hyperbolic trig lobotomy momentarily. What would you do? Like, I'm not licensed to do that in this state. What's that? No? Trig sub, no, let us, you guys, come on. Let me write it this way. This is u minus 1 times u plus 1, yeah? So this could be, yeah. Now, you guys are like thinking about trig substitution. That's not, I'm not dissatisfied with that. That's another alternate route. I'm just trying to get us to go down this path at the moment. And what is A and B here? I say it's clear that it's 1/2 over u minus 1 minus 1/2 over u plus 1, because you can make a common denominator there and see it works out. I mean, yeah, you go through the algebra, but that is what the partial fractions works out to. If you put u plus 1 on the first one, if you put u minus 1 on the second one, the u's cancel, and you get a half plus a half, which gets us back to where we started. So that is the partial fraction, the partial fractioning. And so this is 1/2, 1 over u minus 1, minus 1 over u plus 1, which of course we can integrate and get 1/2 natural log absolute value of u, which was what, cosine x, minus 1/2 natural log, oh, forgot my what? Minus 1, yeah? Minus the natural log absolute value of cosine of x plus 1 plus a constant. And there you go. That would be an alternative way to do this problem. That wouldn't involve a rather, non-obvious u substitution. You're like, well, this involves a non-obvious step as well, right? Like this step maybe is not obvious. Multiplying by sine over sine. But these are the kind of things you want to try to do. If you're facing an integral of a trig function, you got to try to work your way back to sine, cosine, or secant tangent. You got to pick your poison, right? So anyway, let me stop going through stuff. Is there a question in particular somebody has? Yeah.
Are we going to have to do the error that we want for the midpoint trapezoid?
No, I don't expect you to know the error estimates by heart, but you might have to bound an error. So apply it, yes. Memorize the error bounds, no. So I might ask a question like we did in class where I spent like a half hour deriving the m using Calc 1, right? It's possible, yeah.
Same with the numerical integration, like the midpoint and the left point.
Right, numerical integration, I'm interested in you guys having a qualitative understanding of it, but I wouldn't actually ask you to calculate like a left or a right or a midpoint or anything. I think it suffices to give you qualitative questions about those. So as long as you understand the pictures that we drew, you should be able to answer my question if I was to ask one. Of course, the error question, basically the heart of the error question is whether or not you can find the bound on the function, right? And learning how to bound functions is on our list of things to do this semester, so it's a possibility. That keeps coming up, finding bounds. It's underemphasized in Calc 1, but it's actually kind of an important calculus idea. Yeah. Other questions? You guys are, yep.
I think I'm just a little confused after you do like a trig substitution or something, and then you get back a trig function with the inverse trig function on the inside, how to turn it back into something recognizable.
Let's see here if I can find one like that. Yeah, I know what you're saying. The triangle thing, yes. I have a couple of those later on here. Let's see here. Here's one. Problem 11 on the math battle. X squared minus 9 over x. So I made a x equals to 3 secant substitution, right? And that worked out nice, right? Integral of tangent squared. That's not bad at all. It looks scary, though, until you realize, wait a minute, that's secant squared minus 1, and secant squared is elementary, right? So we know that the integral of secant squared is tangent. So we get 3 tangent theta minus 3 theta. Now, when I see something like this, I usually refer to this as a naked theta. It's just theta sitting out there. There's no clothes on it. It's just, it can't be fixed, right? This will involve an inverse trig function as an answer. It's unavoidable. You do have options, though. You could write this inverse secant of x over 3 because of, well, the definition of this x and theta was that x was 3 secant theta, which means secant theta is x over 3, right? Solve for secant theta. So if I look at this and I take the inverse secant of both sides, that gives me this formula. Does that make sense? I mean, that makes sense. This is not the thing you're confused about. You're more wondering where on earth this came from, right? And so it's very simple, actually. So once we identify what the yeah.
How did you draw the triangle? You can answer after that.
Yes, how do we draw the triangle? Very good question. About to explain. So secant theta is x over 3, right? So what is secant theta? One over cosine theta, right? We can also look at it as hypotenuse over adjacent. So that's how I look at it in order to write the triangle. I think, okay, so I'm going to make my hypotenuse x. I'm going to make my adjacent side 3. And then Pythagorean theorem does the rest. Although it's always going to be whatever we try to get rid of, like 99% of the examples. And that's it. And then once I have that, what's tangent theta? Well, tangent theta is opposite over adjacent, right? So opposite over adjacent, tangent theta, just that. Now, but just to weird you guys out, I'm like, I mean, you get your calculator out, try to calculate an inverse secant 3 or whatever, inverse secant is something. Go look for the inverse secant button on your calculator. Good luck, right? There is no inverse secant button on your calculator. So what if you wanted a formula you could actually use with calculators? We always should think of the robot holocaust, right? You never know when the singularity is going to happen and the machines are going to become evil. But, you know, the calculators, on the other hand, at least the one I have, it will always be our friend. Skynet can never get to this calculator, right? It's got no Wi-Fi. So whatever functions are on this are useful to us, as they cannot be co-opted by the evil machines. For example, inverse tangent is on this calculator. See, I've thought about these things. So for the sake of future warfare with machines, that's why I write inverse tangent here, like that. Oh, and 3's cancel, yeah, in less exciting news. But it's impossible, at least for me, to write the answer here in terms of purely algebraic functions. Like that naked theta means that there is going to be an inverse tangent in the answer. Let's look at another one. So here, use trigonometric substitution to calculate this thing. So I had completed the square. I saw, okay, I've got a squared thing plus 1. That's a tangent substitution. So I did x minus 1 equal to square root of 2 tangent theta. And after a little bit of calculation, I end up with like secant theta and then root 2 secant tangent, which is nice because we know secant theta, right? It's not easy, but we know it. It's the natural log of the opposite value of secant plus tangent, right? We got that one. And secant tangent is a basic integral, right? The derivative of secant is secant tangent. So again, I make my triangle. Now, where'd that triangle come from? I've lost it. I've lost it. What was it? X minus 1 equals to what was it? Root 2 tangent theta. Was that my substitution? It was, wasn't it? So tangent theta, I solved for tangent theta. Tangent theta is x minus 1 over root 2. So I think of this as opposite over adjacent. Yeah? And that's why I draw that triangle that I do. I put the opposite side as x minus 1 and the adjacent side is root 2, right? Some of your math majors are like, hey, what do you do that for? You could have done 2x minus 2. And you could have done like 2 root 2, right? And then you'd have like what? What would go up here? Root 2. You could draw this triangle for the substitution as well. There's something you guys never question, which is why is the thing upstairs the opposite side and the thing downstairs the adjacent side? I mean, you could rescale the top and the bottom of the fraction by any number you like, and you'd still have a similar triangle which expresses the same ratios. Let me stop. I'm not helping you. Doesn't matter. Some reason students never have trouble with that. I don't know why. Anyway. It's like the Liate thing. You guys never have trouble with like log being inverse, you know? It's like, what's your problem? It's just your problem. It's not my problem. Now here, you can factor out a 1 over root 2, which means you can get rid of it because you can absorb it into the constant. Do you know what I mean by that? So, I mean, I wouldn't take off points, probably. But I might add a bonus point if you did box the answer rather than put the line above, because it illustrates that you have a good grasp, a deep understanding, deep is probably the wrong word, but a good understanding of logs and what your freedoms and abilities are here in finding antiderivatives, namely that you can adjust the constant to suit your fancy. So if I have stuff divided by root 2, properties of logs say that that's the natural log of stuff minus the natural log of 2. Which means I could take that natural log of 2 and just lump it into a c tilde, right? Redefine the constant. It's not, the answer is no different in terms of, you know, possibilities, and yet it's cleaner, right? So when you have a division by a bunch of stuff in a log, you can, and we're talking about anti-differentiation, you can take that and absorb it into the constant. So, yeah, okay, fine, you get a bonus point on my test. The larger point to tell you about this is so that you can understand answers in books where they make the simplification, and if you're not aware of it, it could make you think that you're wrong when you're not wrong. They've just made a simplification you weren't aware of, yeah? That's all. Other questions? I think I've talked enough about the triangle now. If I talk more, I'm going to confuse you, right? It is in my powers. I sometimes do this thing where I plug in, sometimes do this thing where I plug in I to find constants when there's like a quadratic. Do you have to do that? The answer is no, certainly not. I didn't do it over here today, right? Today, rather than plugging in w equals to I plugged in w equals to 1 and minus 1. Why did I put w equals to 1 and minus 1 here? Because it works, yeah. Because I'm lazy. Because calculating what happens with 1 or minus 1 in this expression is a piece of cake, right? 1 squared, 1. Minus 1 squared, 1. So I knew I had a 2 here, both times. And also over here, with a 1, it's plus b. With a minus 1, it's minus b. And I also know that that's going to give me equations with plus or minus b, which when I add them, it makes them nice, right? So 1 and minus 1 are nice to use when they haven't already been used. And the gentleman in the back told me I should equate coefficients, and that the other day. That's also a good method, right? I mean, there are different choices. Yeah, choices. Partial. You guys ready for the partial fractions? Here, let's look at an old test. What year do you want? Last year. That's not very adventurous. Wait a minute, I didn't teach this last year. Looks like you got 11, 16, 17. We'll go with 17. You guys are cute. As if I'd have your test written already. The weekend where I didn't have time to grade your homework is also the weekend where I have not written your test yet. Yes, here's a good one.
Because the final in the study guide didn't match.
Yeah. Here we go. Set up but don't find the partial fractions decomposition for. Yeah, there's long division in this one. That's not what I wanted to show you right now. Anyway, once you've done the long division, what happens? Ooh, I didn't do the long division. That's not cool. Ooh. Take points off my test. It's not good. We looked at the wrong year. Let's see here. Let's look at a different year. We'll time travel to 2016. A simpler time. Time of possibilities. Let's see here. Where was I? Oh yeah, test 1. Is that a test? That looks like a test. What we got here? Find the area of an ellipse. Oh, look, I did that, didn't I? Ooh, forced a hyperbolic substitution, did I? What do you know? Here's one. Here we got, so what are we looking at? We're looking at, if you complete the square, you've got x plus 1 squared plus 1. So the first thing is irreducible. The second one is what? That's x plus 1 squared. So that's actually x plus 1 to the 4th power. And so the partial fractions decomposition for that would look something like a x plus 1 plus b over x plus 1 squared plus 1 plus c over x plus 1 plus d over x plus 1 squared plus e over x plus 1 cubed plus f over x plus 1 to the 4th. Because the denominator factors into x plus 1 squared plus 1 times x plus 1 squared squared. That's what I'm looking at there. And so the fact that the fact that the denominator factors in that way tells me that partial fractions decomposition. Right? So just a reminder, think about the possibilities there. Yep.
For example, instead of saying a x plus 1, we said a x.
Oh yeah, I wouldn't take off. That'd be fine. I would give you full credit for that. Many books say that that's the partial fractions. I just write that because it makes my integration easier. It brings me back to the substitution that Hannah was asking about earlier, that denominator substitution. Well, guys, I'll see you tomorrow.